Welcome, everyone. I'm Leanna Vicari, co-director of the National Academies of Sciences, Engineering, and Medicine's Roundtable on Plastics. It's my distinct pleasure to welcome you to our Plastics 101 webinar series. The topic of today's webinar is plastics design and production, where we will explore the state of knowledge on plastic design and plastic production to support future conversations at the Roundtable on sustainability and the circularity of plastics. Thanks to those of you who attended our first webinar last month focused on what are plastics. The recording from the first webinar is now available on our event website, and the next webinar in the series will be in December with a focus on plastic use and demand. To register for these events, watch event recordings, and stay up to date on Roundtable activities, you can navigate to nationalacademies.org/our-work/roundtable-on-plastics or via this QR code. For today's session, we will be using slido.com to manage our Q&A. You can access Slido using the widget on the event page, or you can navigate to Slido on a separate device and enter the code #plastic-design and production. There will be a Q&A for all panelists around 1:30 p.m. Eastern. Feel free to add questions at any time, but please bear in mind we will not have time to answer all questions live, and the moderator and panel will have prerogative on topics discussed. I'd also like to highlight that views and opinions expressed during this webinar are solely those of our expert contributors. Now I'd like to hand things off to the co-chair for the Roundtable on Plastics, LaShonda Corley, Distinguished Professor of Engineering at the University of Delaware. LaShonda.
Hello, everyone. My name is LaShonda Corley. I am a professor at the University of Delaware, Material Science and Engineering and Chemical and Biomolecular Engineering, and I also direct the Center for Plastics Innovation. I'm delighted to serve as co-chair of this Plastics Roundtable along with Jenna Jambak. It is my great pleasure to welcome everyone to the second installment of the Plastics 101 webinar series, Plastics Design and Production. A cornerstone of this discussion is the intersection of the current state of plastics design and production and how these processes may contribute to health and environmental impacts in communities, as well as the role of policy in plastics production and design. The Plastics Roundtable is committed to communicating key scientific concepts that are critical to advancing systems-level solutions across all aspects of advancing plastic sustainability. The committee has organized this webinar series to provide information not only for our Roundtable participants in our future work, who come from a wide variety of backgrounds, but also to the public, including the ability to ask questions and to engage with our incredible list of speakers and panelists. We are delighted to hear from our distinguished speakers and panelists today and to enrich the discussion with questions from participants. I hope that you'll find this webinar both engaging and informative. Thank you.
Hello, my name is Hilda Buss. I am a managing engineer at Exponent, and it is with great pleasure that I welcome all of you to today's second webinar in the Plastics 101 series, Plastic Design and Production. I am excited to serve as your moderator in today's discussion, but first want to thank the rest of the working group for this webinar, Veena Singla from Columbia University, Babli Kapoor from Dow Chemical, and Justin Whitfield from Technology Greenhouse, as well as Emi Kamayama from the National Academies. We as a society are challenged with the global problem of plastic waste. Today's webinar explores only one aspect of this problem, the design and production of plastics. This webinar features experts who discuss a lot of different viewpoints on plastic design and production, ranging from a material science perspective, a process perspective, to the impacts of plastics on communities, as well as legal aspects. I think we've all come to rely on plastics in many aspects of our everyday lives, especially in things like food packaging, medicine, construction, transportation, lots of things. Plastics are highly engineered materials that achieve stringent performance metrics. They're carefully produced, and they enable really unique performance in a wide variety of applications. However, we see that the benefits of plastics are often discussed without acknowledging that the costs and benefits of plastics are not evenly distributed in the United States. Communities with low socioeconomic status disproportionately bear the health and environmental costs, while higher socioeconomic status communities receive more of the benefits of plastics. This webinar aims to bring together a diversity of perspectives to help inform future improvements for everyone. So with that, let's get to our amazing panel of experts. I am delighted to introduce our first speaker on plastic design, the current state of knowledge, Katrina Knauer. Kat is the Chief Technology Officer of the Bio-Optimized Technologies to Keep Thermoplastics Out of Landfills and the Environment, BOTTLE Consortium at the National Renewable Energy Lab. Kat, thank you for joining us.
Great. Thank you so much for having me. Can I just get confirmation you guys can hear me and everything looks okay? Great. Thanks, Hilda. I'm thrilled to be here and be a part of this excellent webinar series. So thank you so much to the National Academies, as well as the organizers who are putting on this excellent series. And today I want to talk to you about what we're doing from the Department of Energy and National Lab point of view and perspective in terms of developing novel technologies for plastics redesign and recycling. So I am Katrina, or Kat Knauer. I'm a polymer chemist by training and a senior researcher at the National Renewable Energy Laboratory, or NREL. And as Hilda mentioned, the Chief Technology Officer of the BOTTLE Consortium that I'll be introducing today and telling you all about. But for those who are unfamiliar with NREL, just very quickly, we're based out of Golden, Colorado, right at the foothills of the Rocky Mountains. And we're in the peak of fall color change right now. So it's actually quite lovely here at the moment. And for those who are unfamiliar with the National Lab System, we are a U.S. Department of Energy nonprofit research institution. So there's 13 Department of Energy national labs across the U.S., and NREL historically was very focused on the renewable energy piece and biomass conversion piece. But more recently, we've shifted into a major focus as well in plastic circularity and decarbonization. The reason the Department of Energy is now hyper-focused on the circularization of plastics materials is because there's an incredibly strong intersection between plastics and climate. We tend to look at plastics as a very visible and physical pollution, but in reality, that pollution spans beyond just the materials we're seeing in our oceans and waterways. There's an enormous amount of greenhouse gas emissions associated with the production, use, and disposal of plastics on an annual basis. And to put this into some perspective, the amount of greenhouse gas emissions that we produce from the production of plastics is nearly twice that of the entire aviation sector. And so when we think about decarbonization, we tend to look a lot at transportation and electrification of transportation or sustainable aviation fuels as big targets towards that goal. However, plastics could actually make a bigger dent in terms of climate mitigation. And if we could develop technologies that can reduce our reliance on fossil fuels, reduce the emissions associated with plastics, we have a stronger chance of reducing the rate of climate change and the annual emissions associated with these technologies. So this is why the Department of Energy has invested into this space, and this is why the BOTTLE Consortium was created. And I always like to preface with this because we do tend to get some questions about where is that intersection between Department of Energy and plastics, and this is the reason. And so BOTTLE was created in 2021. As Hilda mentioned, this is an acronym. Department, as a national lab, we always love our acronyms, but it stands for Bio-Optimized Technologies to Keep Thermoplastics Out of Landfills in the Environment. We thought this was quite clever. However, it tends to create some confusion as people tend to think we only work in plastic bottles. That is certainly not the case. We are working across multiple waste streams beyond just single-use plastics. And the whole point of BOTTLE is to achieve what I think everyone on this webinar wants to get to, which is that transition from the linear take, make, waste model that we've been in with plastics for quite some time into a circular economy model where we take raw materials from the earth, whether that be petroleum or agricultural or bio-based feedstocks, and we keep those carbons in infinite circulation. And we do this through innovations, through recycling, redesigning, upcycling, multiple strategies here. And so this is the point of the BOTTLE Consortium and why we were created. We're based out of NREL, but we are a consortium of 8 institutions across the country, all bringing in expertise to this very important topic. And this is really where we focus our efforts in the Bottle Consortium. So we have three major research pillars that we spend our research efforts around. So I mentioned we work across multiple plastic waste streams, not just single-use plastics. We also have a major focus and investment in textile waste mitigation, as well as more complicated waste streams like in cosmetics and personal care, and then even electronics waste. And we've now started to work into thermosetting systems and high-performance materials as well. So our first major research pillar is deconstruction. This is where we're trying to develop catalytic and selective technologies to break bonds in plastic waste streams in such a way that we can use very low energy inputs, low emissions, and get highly controlled product distributions and species from that deconstruction technology. So this is a lot of catalysis, reaction engineering, all focused in the deconstruction piece. The second is then building blocks. And this is where we focus on, okay, we've made a soup of molecules. Now, what the heck do we do with that? And how do we isolate value and isolate monomers and other building blocks in high enough purity for subsequent reuse without ruining the economics of the recycling process or putting in enormous energy inputs that would lead to subsequent emissions? And this is also where our vision is, where ultimately we can start combining waste carbon from plastics with waste carbon from biomass as well. Plastics and biomass waste have a lot in common. Highly mixed heterogeneous materials with aromatic species and other complicated molecules. And one day, hopefully, as we move away from our reliance on fossil fuels, we can start relying more on carbons from both plastic waste and biomass waste. So that's kind of our big pie in the sky dream. But building blocks is really a lot of separation science, separation engineering and unit operations. But this is where we're trying to also combine biology in such a way that we can use microbes as tiny chemical engineering factories for us to do some of the heavy lifting. And then our final research pillar is called redesign. And this is where we're trying to redesign materials for the future to be more intrinsically recyclable by design. And I'm going to talk about how we define that in just a few slides. But I want to emphasize that we are also very analysis driven in the Bottle Consortium. So we rely heavily on techno-economic analysis and life cycle assessment data to drive the work that we do in Bottle. And I wanted to touch on this wonderful study done by the Bardot group at ETH Zurich back in 2021, where they did a planetary boundary analysis and life cycle assessment study to determine whether it would be possible to get to a net zero emissions plastics supply chain. And they found that this is possible to achieve, but it's going to require a lot of work and a lot of innovations to happen in tandem together. And so ultimately, some of the main findings of this study was that to achieve a net zero emissions plastic supply chain, we need to combine a high utilization of bio-based feedstocks. We need more biogenic carbon in plastic materials, but that's not enough. We have to combine that with high recycling rates. So the study showed that to get to net zero, we need this high combination of biomass, carbon capture utilization, and recycling rates of nearly 70%. And so I always like to show this at the very beginning too, because this is really the goal. Bring in more bio-based feedstocks, but also allow for higher recycling rates of these materials. And TEA, LCA, as I mentioned before, this is tools that we're using early and often in the Bottle Consortium to guide both the redesign piece, any new materials we're making, as well as the recycling piece. And so this is just giving you all a kind of placemat view of how we approach TEA and LCA modeling. So we always start with building a process model. We are using Aspen as our process modeling platform for this. There's a lot of other ones out there to use, but this is one of the more common technologies available. And so building out a process flow diagram in Aspen, this is really the heavy lift. This is the hardest part of the whole process. But once you have your process fully designed, Aspen will then generate all of your mass balance, energy balance, input and output, energy and costs needed. And from this, you can generate your techno-economic analysis, where you can calculate that minimum selling price or MSP of your product. So this is very important, because whether you're developing a new recycling technology or you're making a new recyclable by design materials, you need to show a cost competitive, highly economically favorable process. No one's going to be doing this philanthropically. There has to be some benefit and some money to be made at the end of the day. So TEA is kind of the first step. But once this is done, you can use background LCA data from databases such as EcoInvent. So this is where you get the LCA impact of all of your raw materials and all the inputs going into your process. And then finally, using LCA analysis software such as SEMA Pro or Brightway, you can conduct a full life cycle assessment where you look at not only greenhouse gas emissions of the technology, but you also explore the ecotoxicity, eutrophication, acidification, all the environmental impacts of the process. And a postdoc in our team, or not a postdoc now, but a researcher, Taylor Eckert, drew these beautiful pictures to kind of demonstrate what LCA measures. And I think that I like to show her artwork, so I love to include that in there. But this is how we're doing a TCA LCA modeling approach. And I want to then talk about how we're thinking about recyclable by design materials for the future. A big focus of this webinar is what does that mean to think about redesigning materials and new materials that are going to be more sustainable. And so we have a definition here that we've adopted both in the Bottle Consortium and within the DOE of this recyclable by design balance and how we're defining this as we move into the future of circularity. And the first part is what we're referring to as depolymerizability. So we're moving a bit away from mechanical recycling, and that's not because it doesn't have an incredibly important role. Mechanical recycling needs to continue, but it does have a significant limit in terms of true carbon circularity. And so as we think about the future of materials, if we can build in an easier process to unzip these materials back to their parent building blocks, this will reduce energy inputs needed and reduce costs, and ultimately improve the economics around waste collection, sortation, and recycling as a whole. And so our first goal is always recycling, but we're looking at it as how do you make it easier to unzip these materials back to their building blocks and do this in an infinite cycle without loss of properties. So that's goal number one. However, our second goal is to learn from the mistakes of the past. As polymer chemists, we have a responsibility to society to recognize the fact that we developed materials that were littered and leached into the environment that do not have natural putative pathways for biodegradation. And I know some people hear the word biodegradability and it kind of creates a little bit of a red flag because there's confusion around that terminology. And I want to point out that we're not trying to make readily biodegradable materials. We're trying to build in a backup plan to these materials for if they are littered or leached to our natural world. This is going to happen even if recycling is absolutely perfect. And so we have to build in some mitigation plans and design materials that maybe in the span of 4 years rather than 400 years can break down to benign products. So this is the delicate balance we're trying to bring in to redesign materials. And one of the target substrates we think about a lot here is polyesters. The reason we think about polyesters in this redesign space is because a lot of polyesters can be derived from bio-based building blocks. So many of these polyesters that I'm showing on the bottom have biogenic alternatives to make these backbones. Polyesters exist in nature and many of these types of structures can have a biocompatible polymer backbone. And then ester bonds are much easier to break and selectively break than robust carbon-carbon bonds that we find in the most popular plastics used today, such as polyethylene. And I'm not saying that these materials are all biodegradable in the natural environment in terms of how we normally define it within 90 days or 100 days, but most of these kind of bio-based or partially bio-based polyesters have much shorter half-lives in our natural world than conventional plastics used today. So they do kind of bring in some of that backup plan that I mentioned before. And so we're really interested in polyesters in bottle because of that biogenic component and the fact that it's easier to depolymerize them than conventional polyolefins. And in particular, we're looking a lot at these PHA polymers or polyhydroxyalkanoates. So PHAs are considered the most, quote, biodegradable material on the market today. They've been shown to be very biocompatible and break down in soil, biota, freshwater, marine water, multiple environments, which is why there's been a lot of excitement about these materials and replacing them in things like conventional packaging. And PHAs that are on the market today are conventionally made through this biological production that I'm showing here. So this is where we take a sugar-rich cellulosic-rich bio-based feedstocks that through hydrolysis and acidification break them down into more digestible components that can be fed into a fermentation reaction where a bacteria will then harness and digest those carbons and use as a carbon source to synthesize and build PHA granules. Those are then harvested from the fermentation broth, purified, compounded for formulation, and put into some type of product. There's a lot of opportunities and challenges associated with the way we produce PHAs in this manner. Some of the challenges are that a lot of these feedstocks are competing with food crop, which many across the world are not really in favor of, especially as we have a growing population and a growing food scarcity problem. Other challenges is that the PHAs that are produced from this route, we have no control over things like molecular weight and polymer tacticity and microstructure. These are all things that are very critical to the performance of plastics in their final product form. And because we don't have control over that, unfortunately, these PHAs that are made from this process have very low thermal stability. Their processing windows are very short and they tend to degrade during thermal processing. So the products that they can be used in are quite limited. So this is some of the challenges of this process. We can address these by looking at what we call the chemocatalytic route. So this is where you can synthesize PHAs yourself and impart that precise control over critical polymer properties that can then lead to improved performance in a product use. And the nice thing about this process too is that you can use bio-based or petroleum-based feedstocks to make these materials, which does bring in some supply chain resilience, especially as we have an economy that's going to be very slowly transitioning away from fossil fuels. So this allows us to build materials using existing products today as we transition to more bio-based feedstocks. But what was really nice about the chemocatalytic route is we can control precisely things like stereochemistry, tacticity, molecular weight, and microstructure. And for those of you who don't really know what those words really pertain to, one example of how important tacticity is when we think about polypropylene. Polypropylene is going to be used in your everyday life in something like your yogurt containers, plastic yogurt containers. That is isotactic polypropylene. If you took that exact same polymer and that exact same molecular weight, but you made it atactic, it becomes a completely useless goo that you can't make anything from. So that's why tacticity is so important here. And we want to control that so we can make better performing PHAs that are still highly biocompatible and recyclable and can be put into multiple applications. So this is something we're focusing on a lot in Bottle. And here's one example of some exciting PHA portfolios that we're developing within the Bottle Consortium. So this is some work that was done by Eugene Chen's group at Colorado State University, which is a member of the Bottle Consortium, with Dr. Tang here, who was a postdoc at the time, and then Ethan Quinn, who's a PhD student. We discovered that built from these bio-based succinic acid molecules, so right now succinic acid is available on the market today from biogenic feedstocks, we can convert succinic acid to a portfolio of the cyclic diolide monomers. And what's really cool about this is we can make chemically identical diolides, but just different isomers of them. And why that's important is because if you take all these different isomeric forms of this one single molecule and ring open them, what you get is a whole portfolio of chemically identical PHA backbones, but now have very different properties and very different mechanical performance because of the different tacticity we've imparted from that cyclic starting material. Why we like this is because we now have multiple polymers with a varying performance portfolio, but chemically identical, which will improve recyclability of these materials in the future. And if you look at some of the properties of this, this is a mechanical property stress strain curve of two of the polymers that I'm showing to the left, where one's behaving very similarly like a polyethylene and one's behaving very similarly like a polypropylene. And if we also look at their melt transitions, we're seeing melts around the same area as polyolefins as well. So this is also exciting because we want to have more drop-in style solutions to polyolefins that are bio-based and more recyclable, and perhaps this is offering an alternative there. And another reason we're very excited about this is when we think about challenges associated with multi-layer film sachet packaging. So sachet packaging, as I'm showing over here, is an example These are going to be like those ketchup packets or mustard packets that we use. And these are the most overly engineered material you will ever touch in terms of packaging design. These are somewhere along the lines of 8 different layers of materials, all combined together to achieve a very, very specific shelf life of whatever they're storing. And this is actually a beautiful engineering design that was decades and decades in the making to achieve this type of food stability. But it's now led to an environmental crisis in terms of the fact that these materials are completely unrecyclable. Even chemical recycling and pyrolysis recyclers are struggling to maintain or to break down in a safe way these complicated multi-layer films. And perhaps we don't use these as much here in the US, but in developing countries like the Philippines and Indonesia, these sachet packets are a major form of their almost every product they use in their kitchen and their personal care lives. And they make up nearly 50% of their plastic waste streams with no recycling options available to them. And so the reason I bring this up is because that PHA polymer portfolio I showed before, we're excited about the capabilities of applying this to achieve a monomaterial design to something like sachet packaging and food packaging. Can we use this one monomer to make multiple polymers that are chemically identical? So still a multi-layer film design, but those different properties I mentioned before can be combined in such a way to achieve the food preservation that we need and are required from this type of packaging. But now you have essentially a monomaterial product that can be composted, recycled mechanically, or chemically recycled. So multiple end-of-life options, which is really essential for those developing countries as well. So this is something we're actively working on in the Bottle Consortium. We published something on this in One Earth this past year in 2023. And Ethan Quinn is now at NREL doing a 6-month visiting fellowship with us to see if we can create these prototypes. But at the end of the day, to wrap up here, I also want to emphasize what I mentioned before. It's not enough to just be bio-based. You also need to combine this with high recycling rates. So Taylor Eckert, who leads the LCA analysis in the Bottle Consortium and an incredibly talented LCA expert, she and I this past year worked on this kind of study on the life cycle favorability in terms of end-of-life options for PHAs. One of the lowest favorable end-of-life options from an LCA point of view, as you can imagine, is discarding to landfill. These can create methane inside of landfills, which is bad news and a worse greenhouse gas than CO2. The second worst is going to be littering in regular natural environments and letting these leach to the natural environments. We certainly don't want that to happen. Composting does offer some benefits, but it turns out that from an LCA point of view, we're kind of confirming what the Bardot study said, that really we need to be recycling these materials to achieve the most favorable life cycle assessment viewpoint here. So we want to bring in biopolymers to the market, but we also want to recycle them. And this is something that's also important as US composters are now banning compostable plastics for many reasons that I'm happy to discuss today. But this is becoming a limited end-of-life option for bioplastics, so we need other solutions if we want to keep them in circulation. And so our ultimate vision, what I'm showing here, is developing technologies that can handle mixtures of bio-based and fossil-based polyesters in a mixed feedstock so that we can enable full circularity of these materials, hopefully enable high recycling rates, and get us closer and closer to that net zero emissions plastics economy that I mentioned before. And this is our vision from the Bottle Consortium point of view and across many groups within the consortium, is to achieve this at scale. And we recently spun off this technology of mixed polyester recycling into a startup company called EsterCycle. Dr. Julia Curley, who was a postdoc in Bottle, is now the CEO and founder of EsterCycle here. And this is just showing you kind of our process model of what this would look like at scale. Here we just modeled a PLA, PBAT, PET feedstock. We're expanding this to other bioplastics now and working with companies like Glacier and Recology to trial bioplastic sortation at the MRF. And just for some perspective in terms of TEA and LCA impacts, we completed a comprehensive study of this last year. This is currently in revision for publication, but we've seen major benefits in recycling bioplastics, both economically and environmentally. So with that, I will wrap up and thank you all again for the opportunity to present on our work today. And I think we'll be saving questions towards the panel at the end.
Thank you so much, Kat. That was really exciting and super informative. There are already a bunch of questions, but let's hold those to the end so we can make sure that we get through all of our presentations. But thank you so much. I'm now excited to introduce our next speaker, Holli Alexander. Holli is a Strategic Initiatives Manager in Eastman Circular Advocacy Organization. Holli will speak about opportunities and challenges relating to plastic production. Holli, thank you for joining us and take it away.
Fantastic. Thank you so much, Hilda. And I really appreciate the opportunity to spend some time with all of you today here. And thank you so much to the National Academies for the opportunity. I assume everybody can hear and see everything. Please just send me a message or let me know if that's not the case. But again, my name is Holli Alexander. I work for a company called Eastman. We are based in Northeast Tennessee. We're a 100-year-old company, and we are in the process of realizing a circular economy with the materials and the things that we are producing there. A couple of things I want to talk to you guys about today. We'll go a little bit into what we're working on around molecular recycling, but also talking about the broader issue and challenge with plastics. A couple of things here. Let me advance to my next slide. Great. So, and as Kat mentioned as well in her presentation, there are a lot of benefits and values that go with plastics, and I won't belabor this or spend a lot of time on this topic here, but as we think about getting food to people, moving water appropriately, offering healthcare benefits, and protecting people, plastics often turn out to be one of the best materials there to do this. However, we have a very, very significant waste challenge that Kat alluded to as well. For today, globally, only 16% of plastics on an annual basis are collected for recycling, and that's generally going through mechanical recycling today. With that, though, only about 12% of those materials are actually going back into new products. So we have a significant issue as we start looking at 40% of materials that go to landfill, 25% get incinerated, and we end up with 19% that are actually leaked into the environment. So determining how we can start to create new options for these materials is absolutely essential. One area with this too that comes up quite often, it's like if plastics are so challenging and we've got so many issues as we're looking at recycling, why don't we switch to other materials? And it's important to always take a step back and remember why in many cases plastics are being used today. In many cases, they are offering supreme affordability for products, especially as we're going with emerging middle class. We also have a significant benefit that happens that Kat alluded to too around transportation, lighter weight materials, and that versatility. When we start thinking about PET, so one of the major plastics that's used for packaging today, so for those of you who are less familiar with the plastic industry, that's going to be like your soda bottles, your water bottles, and it generally is going to have a resin ID code of a 1 underneath or on the bottom of the package. When we start looking at PET compared to other materials, with aluminum and with glass, you end up with pretty different performance when it comes to energy intensiveness and greenhouse gas emissions that go along with those materials. You also have some particular challenges that happen with mining for bauxite. And then you also have particular issues, and that's for the aluminum side. And on the glass side, you also have pretty big challenges on the recycling side with breakage and the fragmentation of the glass. Suffice to say, there's not a perfect material out there. All materials have them, and what we all have to do is to really start to endeavor to make sure that we are picking the right materials for the right applications, and that has to include end of life or creating a circular pathway for that product. So as Eastman is looking at this, we really focus on determining how we can help support and enable the waste hierarchy. And we focus on this by first looking at what are our options to reduce or eliminate plastics. In some cases, this is lightweighting on applications. In some cases, it's transitioning and removing different parts of packaging and things like that to still get the same performance that's required. We're also looking very heavily at reuse model. So being able to take products and instead of recycling them after one use, can we wash, prepare that, and then keep using that same container, that same device, and be able at that point in time to just keep those items in circulation in their form. Once something does meet the end of its useful life, it will need to go into recycling. And in some cases, we look at options for recovery for certain materials where you might be generating power or electricity or something beneficial or fuel out of those molecules that have been used, but then you also look at disposal. Now, as Eastman is engaging in this space, let's talk a little bit about recycling here. And Kat did a great job of digging into this a little bit. I'm going to go just a touch deeper, I think. Two processes for recycling, or let's say two groupings of technologies that are out there right now for recycling. One is what we're most familiar with, and that's mechanical recycling. Mechanical recycling is great because it has a lower greenhouse gas emission associated with it, a lower energy, because what you do is you essentially take a collection of different products that are very similar to each other, like let's say a bale of clear soda bottles. You take those together, you chop them up, you wash them, and then you can remelt that plastic and make a new product out of it. This is a fantastic process to use, but there's some limitations that go along with the creation of the stream of material and making sure that you have all of the plastics are the same, that they're the same in terms of like color and some of those to make sure that they process appropriately. You also start to get performance limitations over time with each heat history for plastics. Every time it gets melted, it changes a little bit. And so you'll start to see degradation and some aesthetic changes that will happen each time it's used. Now, molecular recycling, this is the term that Eastman uses for it. You'll hear people referring to this grouping of different technologies as advanced recycling, chemical recycling. Eastman uses the term molecular recycling, so that will likely be the term I'll use going through. But these reference kind of a grouping of a variety of technologies. And depending on the technology, you generally are going to have a better opportunity to take a broader mix of materials that may not be viable candidates for mechanical recycling today. As we are looking at it from an Eastman standpoint, we are making sure that any technology that we employ, we're not going to do something that is going to have a worse environmental footprint or greenhouse gas emissions profile associated with that compared to virgin manufacturing. The other thing too that really helps with these technologies is it allows you to avoid some of the performance trade-offs that happen with mechanical recycling, giving us a chance to kind of infinitely recycle and be able to create products that are indistinguishable from prime. Okay, let's dig in just a touch deeper when we look at the waste hierarchy. A couple of things here as you look at different types of technologies. So within this first box here, you'll see that there's a variety of different technologies on the recycling side. So mechanical recycling, purification, depolymerization that Kat mentioned as well, and then also conversion technologies. Now, conversion technologies will refer to a couple of different technologies. They may refer to gasification or pyrolysis, and they're different. I think in many cases, people think of them as very, very much the same, but they have some very different attributes. An area I would love for folks to start to think about with these technologies is we need to consider what is going into the technology, what process or technology is being employed, and what is coming out. Because, for example, gasification is a conversion technology. With this, if we are putting plastics into that process and producing materials at the end, and Eastman operates this as a material to material recycling process, it gives us a chance then to be able to put recycled content into our acetyl stream on at our facility in Kingsport. Now, other organizations may be using gasification technology, and they might be gasifying a variety of things. It could be bio content, it could be plastics, it could be fossil fuels. And with that conversion technology, then they may be actually producing electricity or power, and that one would count as a recovery technology. Pyrolysis gets a little bit more complicated because it actually kind of straddles that line. And in many cases, and not all, and there's some varieties of different technologies out there, but in many cases for pyrolysis, you will be producing material outputs and electricity or fuels, and fuels in that same process with those inputs coming in. So I think that's where a lot of the complication and the confusion comes with these technologies, depending on how people are looking at these. So let's continue a little bit and go back. So unlike Kat, I am not a polymer scientist, and I suspect we might have a few folks on the phone who are either. And as we start talking about how we're breaking plastics back down into their molecular building blocks, just want to go back and just remind everybody that these are just materials that are made up of different combinations of carbons, hydrogens, and oxygens. And as we look at these different technologies, we'll put them into different formats, and you can see there's a variety of different ones listed on the screen, whether it's PET or polyethylene, got polystyrene, polypropylene. And these are going into many of the different products that people use and touch every day. With molecular recycling, the goal is, instead of leveraging carbons and hydrogens from fossil sources or things that we are mining or digging out of the ground or pumping out of the ground and getting oxygen from the air, we want to get those carbons, hydrogens, and oxygens out of the products that have already been used and then be able to reuse them to make brand new products. So a step deeper into the plastic production process. As you start across the screen, generally the way that plastics are manufactured, since the production part is the area that really wanted to make sure folks understood, generally plastic manufacturing starts with fossil fuel extraction from the earth. We go then through refining, then steam cracking, where we start to break those molecules apart. And from that, companies start to make chemicals. The chemicals then are combined with other chemicals to make intermediates. And from that, we can start to make materials. And that's where we can start to make plastics. Plastics at that point, they're quite often going to be sold as like a pellet. You may have heard the term nurdle, or in some cases powder, depending on the type of material. Those are actually sold then and then molded into products or articles. And then after that, they go into consumer use. As we think about the manufacturing process, the items to the further to the left on your screen are the types of activities that require significantly more greenhouse gas emissions. The energy intensity is much higher, and there's a lot more expense in terms of environmental impact and financial cost in many cases in terms of actually doing those parts of the plastic production process. Now, the other areas we start thinking about this, how can we enable circularity? Obviously, we talked a little bit about reuse. That's always great. If you can have a bottle or a jar that you leave as a bottle or a jar and you keep using it, that's a fantastic way to be able to start to create a circular economy. Mechanical recycling, we talked about. With mechanical recycling, we create a loop where we are actually going back, in many cases, right back into that product or article. So it could be like a bottle-to-bottle recycling process. Now, as we think about depolymerization, which is an area where Eastman is investing right now, as we think about depolymerization and specifically methanolysis for Eastman, this is where we will take those materials and we will be able to go back into material intermediates. And from that, continue back down that process to be able to make new products. Now, with a technology like pyrolysis, it goes back a little bit further too. So in this case, you're going to be producing pie oil or pie gas, which generally pie oil is going to go back and then we'll start kind of into that steam cracking process again. So with different technologies, you have different inputs, you have different outputs, and you have pretty significant different environmental impacts that will go along with those technologies. So let's talk a little bit about what Eastman is doing, and specifically in this methanolysis space. And we're focusing on PET and polyester-based materials. And in this area, what we're doing today is we are starting with working to get materials that are not good candidates for mechanical recycling today. So these are products that are just enough different or maybe not valued by mechanical reclaimers, or in some cases, even a byproduct that comes out of mechanical recycling processes. For example, we're looking at colored and opaque PET. We're looking at thermoforms that may be coming. So if you think about like the little clamshell tray that your blueberries come in, even though those might be clear, they're enough different from a bottle polymer PET that they may not be very well valued by a mechanical reclaimer. But we're also processing purge. There are byproducts that come along with mechanical reclamation process. Green strapping, if you think about the strapping that you see holding things on pallets and moving things down the road, in many cases, those are made out of PET. And after that is used, right now, there's not a good end of life for that, with the exception of technologies like Eastman's with our methanolysis process. We're also processing green bottle bales. We're also processing pre-consumer carpet fiber, which we're very excited about, and then also purge from textiles. The material that's used for bottles and for your blueberry trays, that kind of stuff, is a PET or a polyester, and main material that's used for consumer residential carpeting is polyester. And about 60% of our clothing today is polyester based. So what we're doing is we're starting to create an opportunity for these slightly different, but still in the same family polymers to be able to be recycled together for us to be able to go back to virgin-like quality. So with our process, the way that we do this at Eastman with our methanalysis technology, and this is active. We went live with this technology at the end of March this year, and we're very excited about the work that we've done here. What we're doing is we will take that recovered polyester stream, so that mix of different PET-based products, we run that through a mechanical purification process. And the goal here is we want to sort some things out that may not be polyester, but we also want to do kind of size and densification and get things put into a format that can flow and be conveyed through our process. After that, we go into depolymerization. Now with depolymerization, essentially what we'll do is we will take those polyesters, break them down into their monomer feedstocks, and we'll make dimethyl terephthalate and ethylene glycol, which then go into our polymer production line so that we can make the types of products that many of you are using today. And it'll be comparable, it'll be identical to virgin quality material. The scale of the facility where we're operating today is, and like I said, we've just started up this year. It will process about 110 KMT of plastics annually. That's about 240 million pounds of polyester-based plastic. So if you put that into kind of like water bottles, that would be 11 billion bottles that we could recycle annually in this facility. Also, if you look on the screen, there are a couple of links there. I think the slides will be available for folks afterwards, but we've completed an LCA for our process in Kingsport, Tennessee, and we have that that has been third-party certified or third-party reviews, so it's gone through a critical review process. We have that data out there for folks to take a look at, and then we also have a video if you'd like to just see a little bit more of what the process is. So with this, from an Eastman standpoint, we have been very intentional in terms of how we are looking at where and how our plastics are going to help to create a circular economy, and particularly with the technologies that we're talking about with these molecular recycling technologies. We believe that it's critical that we adhere to some strong principles for ourselves in terms of our performance. First off, we need to make sure that we are adhering to a model of reduce, reuse, recycle. These technologies are not simply an excuse to continue to proliferate the world with more single-use plastics, but it's a way for us to figure out how can we have the right material for the right application, have products that are suited for biodegradation and compostability. How can we have the right materials for durability, dishwasher durability that will last 900 plus cycles, but also how can we have products that or have technologies that can help to be able to bring materials back into a high value. With that, we believe that material to material recycling is critical. If you are not producing more materials, then you are not creating a circular economy. So when you're going back into fuel, going back into energy, those may be very valuable options, but what they are not is an actual way to create circularity. And so we really are focused on material to material recycling processes with high percentages on the conversion rates. Quality of life, absolutely essential here. We're an over 100-year-old company, and we want to ensure that we continue to be a good corporate citizen and a good neighbor in the communities where we operate. So we're looking at technologies. We want to ensure that they are lower greenhouse gas emissions versus virgin, and we want to make sure that we're meeting or exceeding regulatory requirements in those spaces to ensure that we are protecting quality of life for our communities, but also for our employees. And these technologies, we want them to operate in a system that is complementary to mechanical recycling. It's very important that we continue to drive materials that are good candidates for mechanical recycling to go through mechanical recycling because they have a lower greenhouse gas emissions profile associated with them, and it takes less energy. However, we also know that additional technologies are needed. Kat mentioned too, like these have to be economical. If we can't make this work from a financial standpoint, it will not be sustainable. But we also recognize one thing that's very different in this space as there have been a lot of questions and concerns that have emerged around these technologies. We want to ensure that we are transparent. We want to make sure claims that we are making about our products, that they are clear, that they are transparent, and that they are third-party certified as much as we possibly can. And in some cases, creating the certifications to be able to do that, to offer that transparency, because we know there are a lot of questions out there. You'll also see that there's a link if you'd like to learn a little bit more about some options looking at responsible production guidelines. This is a white paper that's been developed by a group of different organizations. And the goal here is, though, is to try to get aligned on what's critical and where we need to go. So with that, I'm just going to say thank you and really look forward to the questions as we go forward. Thanks so much, Hilda.
Hi, thanks so much, Holly. That was super interesting. We have, I know we're going to hold most of our questions for the end, but we have a couple of questions that I think are specific to Holly and Kat. So I might ask one of those and then we can move on. And the question is really around transitioning to some of these newer technologies. And so one of these is for Kat and one of them is for Holly. Kind of given that the likely high dependence of more traditional plastics and that bioplastics and non-bioplastics don't play well together, will the development of biogenic plastics require two separate but parallel waste recycling systems? And then more on the production perspective, how easy or difficult is it to switch to some of these newer process technologies kind of from a practical manufacturing standpoint?
Maybe Holly, I could touch on the polymer, new polymer development piece. So I get this question a lot, and I think it's really valid. We have a bit of a fear that as we introduce new materials, are we introducing more complexity that's going to dig us into a deeper hole than we're in now? And I do think that's incredibly valid. However, I also think that fear comes from a place of, well, we've designed these processes for decades for these plastics only. And what happens when something new comes into the mix? And I think PLA has kind of shown this as an example for a long time. PLA has been on a journey for a very, very long time to say, no, we can be in recycling streams, we can be mechanically recycled, we can play nice with the others. There's challenges there. But I think that with the emergence of these chemical depolymerization technologies, the molecular recycling work Eastman's doing, some of the work we're trying to build up in bottle, the enzymatic recycling technologies others are doing, I think this is what's offering us a route to introduce maybe some of the new materials slowly into some of these systems to start determining early on in the inception rather than later what can be tolerable. Is it possible to do mixed streams as we design these from the beginning? And so that's kind of a flowery way of saying I have hope that new materials can be introduced, especially as we really drive towards getting that combination of bio-based content with high recycling rates. And then maybe I'll let Holly touch on more of implementation of some of the molecular recycling and new processes.
Great, thanks, Kat. Great question. And I think on one of the areas on the recycling side is if we're really going to create a circular economy for materials, we need to collect more plastics than are currently being collected today. And right now, the way that people generally want to deal with contamination is by avoiding putting things into the bin. The problem is in that case is those materials then are not destined to be able to have those molecules be reused or go back into a new product. So the way that we need to start thinking about this is how can we get more materials in the bin, but how can we sort better? How can we ensure that we are driving materials to the right options? There's some really brilliant technologies that are happening at the same time that work is happening, like that Kat's doing, that Eastman is doing on the polymers themselves, but around sortation. And you start looking at the increase of machine learning, artificial intelligence, and robotic sorting, different things like that that help us to do this. Now, there are going to be economic challenges that go along with those, which is where some of the things that, supportive with extended producer responsibility and some of those programs will help us start to drive and to create the infrastructure that we need to get there. But where Eastman is focused right now is on some of the more traditional polymers that are out there, but always love looking at. I feel like it's been, I don't know, 15 years probably that bio-based ethylene glycol has been available for PET.
Yep.
And so those are things we can start to do. What are the ways that we can start to bring those different monomers in that may be bio-based, but then at that point, it's still compatible with the recycling system. So in some cases, you can have the best of both worlds. But
Yep.
you know, the other side of the PET monomer is a little bit trickier to be able to get bio-based for that. So those are
We're getting closer, Holly.
Keep
We're
doing
getting
it, Karen.
closer and closer to bio-based terephthalic acid. I swear that's going to be a commercial reality one day. So
I love it. Thank you
Yes.
so much.
Since we've actually been chatting about bio-based, and I suspect it's already been answered, but one of the questions was, can the specific definition or examples of bio-based feedstocks please be clarified? Since we just had a little bit of a discussion of that, can one of you field that quickly, please?
yes, I do you want to. Sorry, Holly, did you want to touch on
Please.
that? Okay. Yeah, this can be confusing as well because there are processes that agricultural and biological feedstocks go through to create that building block. And sometimes there's concern about, are you using, a petroleum-based intermediate to do the conversion of the lignin or the biomass or whichever to get to that bio-based building block? So is it still bio-based? There's some complicated, processes around it that would probably require a very long discussion. But I will say, a bio-based building block is something that is coming from some kind of biomass or agricultural feedstock that is deconstructed to a small molecule that's funneled into some other production process. And so one of the most kind of notable ways of thinking about that is a bioethanol production. And so that's where we take corn, we hydrolyze the starch inside a corn kernel using enzymes, and then we convert that into ethanol with enzymes in an enzymatic system. And now you have bio-based diesel or whichever fuel or bioethanol that you can then use as a building block for new products. So that's how we define a bio-based feedstock or material.
Perfect. Thank you so much. We will have more questions later. So for now, I am pleased to introduce our next speaker, Michelle Nowlin. Michelle is a clinical professor of law and co-director of the Environmental Law and Policy Clinic at Duke University School of Law. She will speak about the current policy landscape around plastic design and production. Michelle, thank you so much for joining us.
You. And let me just make sure that, let's see here. Can you see the slides?
It's coming up, I think.
Okay, can you see them now?
We see the wrong, so I think you want to flip from presentation mode. Do you have two screens?
I do. Okay, is that better?
Perfect, thank you.
Okay, great. So thanks everybody. Oops. I'm Michelle Nowlin. I'm a clinical professor of law and the co-director of the Environmental Law and Policy Clinic at Duke. We've been investing a lot of resources in the last several years to really understand the plastic pollution problem in more detail, understand what legal and policy tools are available. And so that's what I'm going to be talking about today. As I think your last webinar talked about, plastics are really a problem in terms of impacts from cradle to grave. And, as the National Academy of Sciences report on reckoning with the U.S. role in plastic waste really notes, the U.S. has an outsized role in the global plastic pollution problems. And we're seeing these types of problems all over the map, from, impacts to stream health, to aquatic life, to the areas in which chemical refining and plastics production takes place. And we're seeing a lot of impacts to aquatic life as well. Colleagues of mine at the Duke University Marine Lab have shown that with some of these, the chemical signatures that are given off by plastics, some kind of mimic prey species smells and chemical signatures. And so that confuses the predator species who then mistake those microplastics in particular for feed. A lot of these studies have been done in the lab, but also in the ambient environment with anemone. And so we're seeing, some impacts in that way. A study that was released earlier this week talks about how when whales are looking for prey, the acoustic signature that ocean plastics convey mimic those of actual prey species. And so we're seeing an explanation emerging anyway for the rates of ingestion in a lot of marine life. And so these are, among many of the reasons that we want to address this problem. The other significant problem that my clinic students and colleagues have been focused on are the environmental justice considerations and environmental inequities associated not just with plastic waste and disposal, but also with the manufacturing process. Again, that cradle to grave view. The little map on the bottom right of your screen identifies different chemical refining and manufacturing facilities associated with plastics in Louisiana and along the Gulf Coast. And then you see that, along those same corridors where those facilities are located, we see much higher risks of lots of different health problems, including cancer. And we also see demographically that same corridor is populated primarily by people of color, African Americans, Black people. And so what we're seeing is this manifestation of a real serious environmental justice problem because a lot of our permitting processes do not adequately consider the cumulative impact of these multiple exposures from the concentrations of refining and production that we're seeing. It's also a problem, though, of course, on the waste management and disposal end. Here in North Carolina, I live in Durham, North Carolina. Our waste is trucked more than 90 miles away to the southeast to a small community in Sampson County, the Snow Hill community, which is 84% Black. It was that was a similar demographic when the landfills, both unlined and unauthorized, and the more modern landfills were located, and that remains the characteristic of that community now. One significant change, however, has been the loss of economic opportunity and the loss of property values that family or that community has suffered, along with increases in pollution, including PFAS contamination of wells. So we're seeing that, even on the disposal end, where we have significant environmental justice problems. And when we consider the amount of municipal solid waste that is composed of plastic materials, upward of 19 to 20%, we see that connection between plastic waste and communities of color and environmental injustices. One of the other things that we note is that on litter index surveys that we've conducted around the community, high areas of plastic debris correlate with formerly redlined areas within the communities. And GIS analysis indicates that is the result of continuing underinvestment in those communities that began with the redlining phase more than 70 years ago. So we see thoroughfares with higher speed limits. We see a proliferation of takeout dining facilities, fast food chains, convenience stores, and a lack of investment in waste management infrastructure. So all of this correlates to have a significant impact and problem in terms of environmental injustices. So if you think about the plastics life cycle, as the two previous speakers have done, you think about where our interventions tend to take place. We talk about the need to improve recycling. We talk about improved waste management infrastructure. We talk about stormwater controls, better recycling, and then also the imposition of fines for littering and a heck of a lot of volunteer effort going into to cleaning up the waste that accumulates in our environment. And a really significant component of all of that I think is important for us to recognize from a policy perspective is that all of these activities are funded by local governments and taxpayers. So you see again with the amounts of plastic waste that are in that municipal waste chain, a lot of the money that we're spending in terms of our volunteer hours and in terms of our local tax dollars are being spent on trying to properly manage and remove from the environment discarded plastic waste. So that has led to, driving interest in prevention at the local and state levels. On the right part of your screen is a national map with little icons that reflect different policy interventions that state and local governments have been adopting, that Surfrider is tracking around the country. And so what we see are a proliferation of efforts such as bag bans and fees, skip the stuff initiatives, even some reuse mandates for dine-in facilities, bans on the intentional release of balloons, things like that, to really get a little bit higher on that plastic life cycle chain to try to do things around prevention. We also see a lot of innovation on the part of nonprofit organizations, community organizations, and local businesses. So real interest in refill and bulk buying businesses, efforts at schools, at PTAs to try to get rid of plastic utensils and styrofoam trays from the school lunch programs. Lots of NGOs that are looking at how you circulate reusable bags in the communities with a particular focus on those communities that might not be able to afford purchasing those reusable materials. Looking at certifications for local businesses that do their part to really reduce the generation of plastic waste. And even coalitions with partnerships with artists to try to do a lot of education around storm drains to try to change public behavior. But again, all of this really puts the onus on the public, and that's pretty costly. And it's also really inefficient because we can't stem the leakage of all the materials simply because of the volume of the materials and the waste streams that are produced. The waste keeps returning to the trash traps in the rivers that we've been working with to try to, quantify the impact and identify where the sources are. You kind of feel like Sisyphus after a while. You go back month after month to try to deal with this problem, only to find that the waste has returned. I even see that on my evening walks around the neighborhood where I, take a plastic bag with me to try to pick up all the trash that we find along the streets. One of the concerns that I think has really limited some of the efforts at that local government level is the real problem of preemption. The states that are highlighted in kind of that purple color on this map are a list of the states that have adopted statewide preemption laws that prevent local governments from doing what they can do to try to stem the tide of plastic waste and reduce waste generation. By preempting local control, what you're really doing is leaving those local communities holding the bag and with far fewer tools to deal with the quantities of waste that we're dealing with. So that's one of the real concerns that we have from a policy perspective that we're seeing around the country. So what can we do about all of this to try to change and try to adopt different methods, different interventions to address plastic waste and really try to drive more innovation and reduction? So the first thing that I like to encourage folks to do is to really think about the different levels of government and what different authorities those levels of government have, what part of the plastics issue they can reasonably deal with from an efficient standpoint. And also think about the different legal tools that are available to maybe associate with the environmental media that you're trying to protect. such as drinking water, the health of aquatic ecosystems, or maybe the safety of limiting food-based exposures. As I discussed already, most of the attention has been paid at the state and local levels on waste management and removal of litter from streets and beaches. And there is a lot of innovation taking place, a lot of progress, but this result is a patchwork of efforts. And that lack of uniformity has created confusion, and I think really contributes to the contamination levels that we see in recycling programs. And I think the most significant aspect of all of this patchwork is that it results in disproportionate burdens that are placed on communities that are located in areas where either the capacity or the political will is lacking to do something about it. So what we really need is a strong national strategy to try to address this problem. I'm encouraged that the Biden administration really is paying attention and doing what it can through the offices in the White House and the issuance of executive orders on sustainability, tackling the climate crisis, and dealing with some of the racial disparities and environmental injustices associated with pollution across the country. So I'm really, really encouraged that the Biden administration, Biden-Harris administration, has centered environmental equity and justice in their responses. In July of this year, the federal government announced a new strategy on mobilizing federal action on plastic pollution with a goal of phasing out the procurement of single-use plastics from all federal operations by 2035, and with an interim goal of reducing or phasing out those single-use plastics from food service operations, events, and packaging by 2027. And this is consistent with the policies that the Department of Interior has adopted and the National Park Service is adopting for reduction of single-use plastics in their land holdings as well and facilities. On the other hand, however, I think that the administration really missed a great opportunity with EPA's draft national strategy to prevent plastic pollution and with General Services Administration proposals for reforming the federal procurement process. Both of these really adopt voluntary programs without specific numerical goals or timelines, and they haven't really taken advantage of some of the existing authorities that those agencies have to really tackle the generation of plastic waste. So that leads to some additional analysis, and perhaps some recommendations for moving forward. So one is to really think about that waste hierarchy. Holli talked about that in her presentation, and I think we need to really be focusing more on the prevention and reduction and not just on the recycling and the recovery and ultimate disposal of these different types of materials. We need to recognize that there is no, 100% sustainable form of packaging. All types of packaging create some impact. And so what we really need to be doing is focusing on increasing reuse systems, extending the product life cycle or lifetime, particularly for large expensive goods, and then improving the recovery of the materials at the end of a product's life, but really focusing in on that prevention and reduction component of it. EPA Administrator Michael Regan has said that we need a transformative vision for a waste management system that is inclusive, more equitable, and reflects the urgency of the climate crisis. And I really couldn't agree with that more. But I think that we need a broader version of what it means to manage that waste, starting up at the very beginning with prevention and reduction to begin with. So I'd like to think about a new type of plastics life cycle, one that begins with oil and gas extraction and thinks about why those materials are so incredibly inexpensive. I've read lots of reports about, that it's less expensive to create virgin plastics than it is to develop materials from recycled products. And one of the reasons I think for that economic calculus is the extraordinary subsidies that we put into fossil fuel development in this country. The International Monetary Fund estimates that was $757 billion in fossil fuel subsidies, excluding coal, in 2022 alone. Now, this includes indirect subsidies, such as some of the negative externalities that we've been talking about, but a lot of that really is indirect subsidies that incentivizes more oil and gas extraction, including from really marginal sources. So that's something that we could do to reduce or eliminate those subsidies and change some of that economic calculus. Now, the Biden-Harris administration's budget proposal for fiscal year 2024 would have eliminated more than 13 fossil fuel tax preferences and credits. And one of the added benefits for perhaps reducing that scale of production would be a reduction of the federal deficit by almost $31 billion. So I think that that's a policy that we could give a lot more time and attention to. Another one is just kind of jumping out of that plastics life cycle structure for a moment is think about federal procurement. The federal government is one of the very largest purchasers of different products and services in the country, spending upward of $750 billion a year on those products and services. So that's a significant driver of the types of things that we can see in terms of our plastics production and waste generation. And by altering some of those procurement strategies, we could really drive a change in product innovation and increase circularity, increase reuse systems, some of the things that earlier speakers have talked about and that a lot of policies are driving for. But looking at those procurement guidelines at both the federal and state levels as well as local levels could really drive a lot of change in terms of what materials are produced, how they're designed, and how they're deployed within the economy. But if we go backwards a little bit after oil and gas production or extraction and think about the chemical refining process and the plastics manufacturing process, we see that we have a lot of existing authorities already in federal law. Now, I'm not going to be able to go over all of those in the interest of time, but I will commend to you a recent report from the Environmental Law Institute that gives a comprehensive view of those different federal authorities with scores of different laws that could be used to address different aspects of this problem. But right here, when we're thinking about chemical refining and plastics manufacturing, we can really start talking about, better deploying the existing authorities that we have under the Toxic Substances Control Act, the Clean Air Act, and the Clean Water Act. One of the things that I really like about the potential for TSCA and better utilization of that statute is that it really focuses at the chemicals and polymers that are used at that point of production and shifts the burden of proof onto the purveyor of those materials to show that their use does not present an unreasonable risk of harm to human health and the environment. And that's really where the burden of proof ought to be. Historically, it was on the EPA to try to identify after those materials were already introduced into commerce and identify which one of those were causing problems, and then initiating a very complicated process for trying to withdraw approvals for those materials after harm had already been created. But with the 2016 amendments to TSCA, that burden of proof has shifted, and so I think that provides a very potent tool for us in thinking about reducing some of these impacts and driving different forms of innovation. One of the other things that we can think about in terms of the permitting for of pollution from the air or from the water is really, again, centering environmental justice, doing a much better job of thinking about the cumulative impacts and the disparate impacts on certain communities. And those authorities already exist within our existing statutory constructs. And our agencies can offer more clear guidance on how to conduct those types of analysis and health assessments through those authorities in the Clean Air Act and the Clean Water Act. If we look at materials and product design, we can think more about good extended producer responsibility programs that, again, place that burden on the manufacturers of their products so that they really think about the full life cycle and the costs that are being imposed on society from their deployment and their convenience. The challenge there is to make sure that appropriate pricing signals are sent so that those manufacturers don't simply make the calculus that it's better for them to just pay a fine than to actually take that full responsibility throughout the product life cycle. We can also look at tools under the Food, Drug, and Cosmetics Act to think about leaching into different chemicals that would be leaching into food products. Excuse me. And other forms of consumer product safety. Excuse me. Finally, when we do think about waste generation and disposal, I think we could do a much better job with a national recycling program that sets standardized terms for what can and cannot be recycled. And I think that that would do a lot to reduce confusion as people move around the country and reduce the contamination of that recycling stream. We can also think about better utilization and enforcement of some of the green guides that the Federal Trade Commission has to make sure that those labels about what is biodegradable or what is actually recyclable have actual meaning and don't end up misleading consumers. So that's kind of a quick overview of different programs, policies that could be used. And I would welcome any questions that you might have at the very end here. Thank you.
Perfect. Thank you so much, Michelle. That was super informative. I'm going to ask you to actually stay because we're going to hop into some questions. Unfortunately, our final speakers, Joy and Joe Banner, are held up right now. If they can, we're going to go into questions now. If they can join us, we will pause questions and hear from them. But I just want to introduce them so that if you have the opportunity to read some of their work separately, you can. So Joy and Joe are co-founders and co-directors of the Descendants Project. The Descendants Project is an emerging organization committed to the intergenerational healing and flourishing of the Black descendant community in the Louisiana River parishes. The lands of the river parishes hold the intersecting histories of enslavement, settler colonization, and environmental degradation. We really hope that they can join us. If they cannot, their website has a lot of information, www.thedescendantsproject.org. So with that, if we could have all of our speakers are already here. Thank you. And since we just finished up, let's maybe have a couple of questions first for Michelle, since your talk is still fresh in our memories. And there's a lot of questions, I think, about controlling for or trying to improve the health impacts, specifically of plastic production. You talked about some of these existing tools, the TSCA, the Clean Air Act, things like that. And how do we make these tools work better for us?
Well, I think, one aspect that we need to consider is that, the tools that are available are only as good as the science that goes into them. And so we need a lot more information about some of the human health impacts of exposure to different chemicals, particularly the microplastics. We're seeing a lot of laboratory studies that show that different wildlife, different marine organisms have negative health impacts from exposure and ingestion of those microplastics. But the same type of information isn't readily available in the human population yet. And a lot of these statutes, the Safe Drinking Water Act, the TSCA, the Clean Air Act, the Clean Water Act, the emission standards, the discharge standards are really predicated on human health exposure. You have to build in an adequate margin of safety for to protect human health and welfare. And so if we don't know what those exposure levels are that cause significant problems, then that makes EPA's job a lot more challenging in terms of setting those standards, or the Food, Drug, and Cosmetics Administration, FDA, setting those standards. And so really improving the types of studies that we're doing, the amount of research that is being done on that on those questions, I think is really important driver here.
Thank you. And then sort of a similar question for you, Michelle. Sort of the newer policies that are coming up, you mentioned some of the EPR laws, some of these. How well do we expect these to work, and on what timeline? You mentioned a little bit on timeline. If you could just maybe comment on those two aspects of some of these newer legislations.
So I think in terms of, policies that really have the most bang for the buck in an immediate sense are thinking about procurement decisions and extended producer responsibility programs, that can be as simple as bottle return bills, things like that. I think that those really have the potential to change the economic calculus and to drive more innovation in terms of product design and circularity of reuse systems. So those are the things that I'm most looking forward to, that I think can have the most immediate impact. Other things like reducing subsidies for oil and gas, I think that would have the most impact, but I'm not sure that the political will is there to address those big ticket items. And so in the meantime, while we chip away at those types of things and try to close those loopholes, focusing on other interventions that can change the economy of the plastics industry and waste systems, I think are really important.
Michelle, I'm sorry. I don't mean to put you on the spot, but a bunch of I think just because your talk was last. Next question.
Well, policy is a lot easier than science.
No, and we'll get to some of those science questions, but they're sort of all grouped together. Do you see the need for changes to RCRA to deal with plastics recycling, especially the challenges posed by Commerce Clause limits on what states can really do?
Yeah, RCRA is something that has a lot of potential that really hasn't been realized at this point. The title of the statute is a bit misleading in thinking about, resource conservation. And that would be a perfect vehicle for having a really beneficial recycling strategy, for example, to have more clear guidelines about what can be disposed in a landfill and what needs to be diverted for material recovery. Those are different types of things that I think could be done pretty easily through RCRA. But again, it would require EPA to be able to do that, and then it would take some time for that to trickle down to the states to be able to incorporate. One of the things that I've been reading about is the potential for classifying microplastics as a hazardous waste, because of the deleterious health impacts and ecosystem-based impacts that microplastics and nanoplastics can have on organisms at all different levels of life. But I think that that is going to take a lot more time than some of these other types of interventions. One thing that could be done to deal with microplastics, perhaps more effectively than thinking about classifying it, going through that process of classifying it as a hazardous waste at this point, might be to incorporate it into the National Ambient Air Quality Standards. We already have a particulate matter standard for those ambient air quality standards. And if they could be tweaked to include microplastics in that process, or think about it in terms of the suspended solids in the water column through wastewater discharge programs under the Clean Water Act. Those are other types of interventions that could still get at that problem, but using different statutory authorities than RCRA.
I think this one is for all of the speakers. On the production side, in addition to reducing overall polymer production, is there one production process, polymer, or product that you think might be low-hanging fruit to address microplastics concerns?
I mean, I think this one's always really tough to answer because we're trying to gather more data on microplastics so that we are making data-driven decisions on how to prevent and mitigate that. However, I think, one thing to consider that I touched on a little bit in the talk that we're trying to do from the Bottle Consortium is building in what we're calling that backup plan. Can we design materials that, if they shed microplastics, do have a pathway to ultimately break down in freshwater and marine water environments to biomass H2O and H2O and CO2. That's not by any means, the solution, because you're still shedding microplastics. But this is also where some of the advanced recycling and molecular recycling technologies that we were talking about could help as well. Mechanical recycling, as I mentioned before, is great for many, many reasons. It can handle clear, natural colored materials quite well, but you are every time slightly degrading this organic material, and it could lead to potentially microplastic formation over time. So maybe as we move more towards the molecular recycling kind of piece that Holli said, and we're going back all the way to building blocks, we could help prevent that in the future in recycled products as well. So I think there's a combination of strategies happening in complementary pathways to think about how to mitigate the long-term recalcitrance and production of microplastics.
Yeah, I'm not sure. I was thinking, like, if I knew what that low-hanging fruit was, I might not be on this call today. But I'm hopeful, right? But I do feel like one of the biggest areas, and I think Michelle and Kat have both referenced this as well, it's like that there's a lot we still don't know, and depending on what the sources of those microplastics are, whether it's coming from paints and coatings, whether it's coming from tires, whether it's coming from packaging, whether it's coming from clothing, the interventions that you would put into place based on the sources of those materials may look very, very different. And so I think really trying to get a handle, in some cases, you hear a lot of these, like, there are microplastics. What kind of microplastics are they? What are they actually made of? Are they absorbing additional chemicals that are in the environment? Are they not? And then what's that source of actual, I guess, ingestion or contact with those? And there's so many things we still don't know. And it feels to me that the challenge is significant enough that we want to make sure that the investments and the interventions that are going into place actually have the impact that we want. That it's going to be important to try to learn as much, I think, as we can so that we have the right solutions in place.
And I'll just chime in. I don't know, what that low-hanging fruit might be from a scientific perspective. But the perspective that I do have is that, while we're waiting for, the science to unfold and for better understanding of what those human health and ecosystem impacts, really, really are, what can we be doing to minimize exposure in the interim? And, are there better screens that we can put on, to capture that microplastic pollution through air emissions that are coming from air emissions, that are coming from plastic packaging, that are coming from wastewater discharges? Can we have municipal water supplies, adopt different filters to screen out microplastics so that we're not getting delivery of microplastics microplastics when we turn the tap on, or there are different filters that you can use on drinking water facilities to prevent and, to trap those microplastics and prevent them from getting through for ingestion. Because my driving concern here is that just like under the old version of TSCA, where, the chemicals were able to be used, they were able to be released into the environment, and then, oops, we've got to try to put that genie back in the bottle. We're playing, we're using we're using our health as the litmus test here as we wait to answer some of these questions. And so I would prefer something that is much more precautionary, much more preventative, and screens out those materials until we know that they are safe.
So I think Joe Banner might have just joined us. Joe, are you here, and are you able to sort of give us some context? We're in Q&A. We can also do a couple more questions to give you some time if that is useful. We already did a quick introduction to you and Joy. But if you're ready, I'll give the floor to you. If you need another minute, I can ask one more question.
No, thank you. And I apologize for being late. My plane was 6 minutes late, and that messed up everything. So yeah, I'm really wish I had my slides up. But yeah, thank you for the opportunity to contribute today. And it's a topic that me and my sister Joy have been very interested in because of course, her role as being a business professor for 8 years and working in marketing and understanding products and packaging, and then also just being in an environmental justice community that's impacted by plastic pollution that comes a lot from packaging. So just to give you an overview for those who may not know who we are, my name is Jo Banner. I'm co-founder of the Descendants Project, and we're based in Louisiana, in St. John the Baptist Parish. My family has been there for over 300 years. I'm 10th generation Louisianian. And I really love my community, deeply rooted in that community. But unfortunately, with all the great things that we have, something we also have to deal with is pollution. We are in an area known as Cancer Alley, which is an 85-mile stretch between New Orleans and Baton Rouge, and St. John Parish is actually right in the middle of that stretch. We have essentially 200 plants in the area, and most of them are focused on producing plastic in some way, shape, or form. So my community suffers a lot from the health impacts from the upstream production of plastic. The chemicals that are used to make the product are created or produced in my community. So the issues that we are dealing with, of course, is cancer is one of the ailments. We also have asthma, we have heart problems, lung problems, skin rashes, just a host of different conditions that our community deals with on the regular. In addition to having that, the ailments, you also have the anxiety that goes along with that. And that's something that we often don't talk about, is the anxiety, the grief that we have to face because we're in such a terrible predicament in terms of pollution. So in addition to petrochemical pollution, we also have pollution that comes from aluminum, and we also have pollution that comes from steel. So although we focus a lot on petrochemical, we also understand, for us anyway, that all of these things are harming us. And that's really because of the heavy industry that was created in our area for sugar in the 1700s. That plantation system that brought in enslaved Africans, that started with the refining of sugar, the proliferation of the refining of sugar, and then sacrificing people for that. So all of this, the zoning that's on the land, but particularly the companies that came in, they settled on these plantation grounds, and they settled in the footprint of that pollution. And that's why they were able to be successful in Louisiana, because they fit right in. Now, communities like mine who descend from the people who were enslaved at the plantations, that's our homes. Like, those plantations were a workspace, but it's also a community, because that was the only community that our ancestors had. So we see our families moving off of those plantations, right? But they would move right alongside of it because that was their home. And so descendant communities like ours who were on the fence line of plantations are now on the fence line of petrochemical companies. So this is having a particular impact on Black descendant communities in Louisiana and other areas too. And you may think, why, Joe, do you focus on that particular type of community? Well, because I am from that community. It's not like pollution doesn't impact everybody, but when we protect the most vulnerable, and everyone gets that protection. So we may be on, we're at ground zero, but everyone else is at ground 0.5. So whenever a community like mine is helped, everyone gets helped. And it's why we really believe in the mission of making sure that we have improvement, particularly for products and how they produce. One issue that we want to bring to light is not just designing, it's also what can we deconstruct? What can we make? What products can we make that doesn't need a package? Can we eliminate those things? What's an essential material that we need? Even working on a list that could say, this is something that is going to be important to us versus a film window on a spaghetti box. So having a list of what do we find is essential, because there's nothing that's going to be produced that doesn't have an impact on a community. There's no solution that's a solution for everyone. So it's really important that when we are producing this, that it's only for the absolute necessary products that we need to produce it for. So I will, that's it for me.
Thank you so much for joining. And I think something that you just were talking about was one of the questions that we had. So I don't know if you want to talk about this a little bit more, but the question is, are there types or applications of plastics that can be scaled down or phased out of production? If so, what kind? For example, berry containers that used to come in post-consumer recycled paper pulp. You gave the example of the window of the spaghetti. Joe, you can field that. Any of our other speakers, if you guys could come back, and if you guys have comments on that too, I think that this is a good time for that question.
I can touch on one topic here that we touched on briefly on the bottle section or part of the talk was multi-layer film production and the sachet packaging, and this is part of what Joe mentioned, the clear window for the spaghetti. And we've developed those materials to achieve really long shelf life of plastics, but we also developed them to be highly branded and marketed. They had to be clear, they had to be printable so that people could put specific branding on there. And those things that we achieved for visual appearance have also created materials that are less and less recyclable. And I totally agree with Joe's sentiment there that every time I talk to the major brands, they claim that's what consumers want. And in reality, is that really true? Can we move away from perfectly clear, optically clear packaging and printed on packaging and make materials that are more recyclable, while we're also simultaneously reducing the amount of packaging that goes into what we use on a daily basis. And I just want to thank Joe. Thank you for everything you said, for what you and your sister are doing. It's incredible work. And I went to school down south in Hattiesburg, Mississippi. So not the same exact area, but near and dear to me, all of Louisiana down there. So thank you.
I think one thing that I'll add to that I think we're going to want to be careful about, and I think everybody has like the molded fiber plastic, or the molded fiber berry containers, and if you go picking somewhere, that's usually what you're going to get and all that, which is fantastic. One of the issues, though, that I think that we've bumped into and we need to be cautious about is ensuring that the packaging that we're using is going to provide the protection of the product on the inside, particularly berries. And I don't know about you guys, but I feel like some days, like, you buy berries, you give them a strange look, and the next thing you know, they're molding. But sometimes you can buy berries and they'll last for like 6 or 7 days in the fridge. And and they've done a lot of investment, many of the organizations. And while that's not necessarily a place that I think Eastman has done a great deal, there's been a lot of investment to ensure that they're basically consuming some of the off gases that come from the berries that speed up decomposition, right, or the aging of the berries. So can we ensure that packaging that we're doing, because the greatest greenhouse gas emission that we're going to have associated with those berries is going to be if the berries don't actually get consumed as opposed to the packaging. However, we have to manage the waste issue at the same time. It can't be a one or the other. It has to be both. But we just need to make sure that when we do make a transition or a change that we aren't creating an unintended consequence. We just need to do it intentionally.
I'll just chime in, as we've been talking about this more, one thing that really could be addressed, I think, is the proliferation of polystyrene packaging, which is particularly when used for food products, is impossible to recycle. There aren't facilities that will take things that have been contaminated with food residue for the recycling process. And then, the leaching of different chemicals, toxic chemicals from that polystyrene into foods, particularly hot foods, is also a real concern from a public health standpoint. And so if there was one thing, that we could do, to address part of this problem, I think it would be to ban that polystyrene from use in food type products. It's also the number one contaminant that we remove from the waterways across North Carolina, by at least, I'd say, 20, 30 times more polystyrene, just because of how it very quickly breaks down into smaller and smaller pellets in the environment. So eliminating that would have, I think, go far towards addressing some of the problems in ecosystems and human health that are posed by plastic waste and packaging.
Yeah, can I just add one more thing there from Michelle? I could not agree more that there are materials that, if I say out loud, I'm going to probably get some pushback from people eventually, but polystyrene, PVC, materials that continue to be used because they're cheap and we can mold them because we can add plasticizers and things that makes them highly amenable to different processing tools, but are incredibly problematic in these recycling streams. And as we think about creating a more monomaterial design, more recyclable feedstocks coming in, increasing what's going to recycling, like Holli said, I do think there are materials that can be phased out. And a big limitation right now is still costs. And I'm hoping we move above that, and EPR hopefully will help with that. But just wanted to say that there are some things that I think are redundant that can be reduced, and we could focus on more recyclable streams like PET and polyolefins.
If I can add to with just having almost lost my hometown to a PVC plant for most of the plastics in the 90s, and now still dealing with the ramifications of the zoning to get that plant to the community, even now, 30 plus years later. Also, just last week, we had 2 workers at Formosa, Louisiana, who were harmed, were injured on the workplace. So you see one side of it, but that's when on the other side of it, when you calculate everything that's going on, the corruption, the collusion, the corporate capture that happens, it's such a dirty business. It is so dirty. And even if the company is doing everything right, there's still a government that usually isn't. And all of those things is what the consumer just doesn't see. And it looks like, oh, we're just going to change the material. There's so much more that goes into that. And even with the example of the berry container, I think it's a good one. But my pushback would, maybe we shouldn't eat berries that can't be grown locally, that we have to put in a package like that, because we're going to have to change the way that we live. We're going to have to start sacrificing so that communities aren't bearing so much burden. And that's where it may not be that we can get raspberries from Norway out of season in Louisiana because we have to put them in containers, so much packaging. So I think that those are the decisions or the questions I want people to start asking, especially when we have engineers, we have system engineers, we have people who do this for a living, and having that brain power put into that type of engineering as well would be very beneficial for fence line communities. Thank you.
Great discussion. Any other thoughts? Yeah, thank you. Our next question that I have lined up here is, from your perspective, what is the single largest challenge or roadblock to improving the various aspects of design and production of plastics?
I really appreciate that the questions are so easy.
I agree.
Yeah, that's I don't know if it's the very biggest, but I think what I will say one of the biggest challenges we have is kind of twofold. Is one of the areas that makes recovery of plastics as complicated as is the fact that they're very lightweight. Another reason that makes them complicated from an end of life scenario is the fact that the materials aren't as valuable. And you put those two things together where they are lightweight and they are not as expensive, then all of a sudden the economics around creating a collection stream or the drive to actually aggregate those streams becomes so much more complicated. Steel is a very different situation, right? Steel and aluminum both are very, very different. Glass a little bit easier because you can get a truckload pretty quickly, but you also have the economic issues that go along with glass. And so as you look at some of the different materials, as we really want to try to create the circular economy, dealing with those issues and challenges with plastics, which is why we chose them in many cases to begin with, also become kind of their detriment at the end of life. Of course, that doesn't address the broader issues around this, which is why I'm not going to say this is the most issue or the most significant issue, but I think that's one of our core challenges.
And I would highlight from the level that I'm at, which is research and development, trying to make recycling technologies alternatives to current conventional plastics. Certainly, the cost is my biggest challenge and our team's biggest challenge, and one we're constantly being faced with and challenged with as we have to set ourselves to the standards of comparing to the price of polyethylene today, which is unbelievably cheap, as we all know, somewhere around the order of 75 cents a kilogram. And so if we make recycled polyethylene, if we make a polyethylene alternative, that is what we're compared to. And that is incredibly difficult to beat. They've had a century to optimize that, while we have had, let's say, 5 to 8 years, in this kind of push towards more circular technologies. And it's incredibly prohibitive because the mindset is so, if you do not meet this price, nothing can be done. While I love to tell people that when polyethylene entered the market back in the 50s, early 50s, it was $4 a kilogram, which with inflation today equates to something like $45 a kilogram, because it was brand new and no one had ever seen it before. And we didn't have enormous production plants of it yet. And so I wish that as a society, we could understand that new is going to mean more money. And with supply and demand and optimization, those costs go down. But it is incredibly prohibitive, both from the recycling point of view and from the redesigning and new alternatives point of view.
One of the roadblocks that I see is, unsurprisingly, a law and policy roadblock. And that is some of the misperceptions about the health benefits of circularity and reuse systems. We often have local departments of health that, kind of freak out and think that, it's impossible to sanitize, plastic, or excuse me, silverware or plates and cups and things like that. That would be posing a public health risk if you were to bring in your own takeout container, for example, at the restaurant. And it's really misplaced concern and fear about all of this that I think worsened with the COVID-19 pandemic. That people are just really reluctant to think about things that haven't been through some sort of chemical sterilization process. And so re-educating public health officials and looking at those types of laws, I think would go a long way to being able to promote more successfully some of these circularity ideas, particularly in the grocery and food spaces.
Perfect. Thank you. Kat, this is a question for you, and I think it is related. Joe, did you want to have something to add? I know your camera is hopping on and off a little bit. To this idea that you said that like new is going to be expensive. So the question is low industrial fermentation capacity for commodity materials hindering the biopolymer alternatives design process? Might other biological methods get us the same desirable toxicity endpoints for PHAs or other materials?
Yes, absolutely, 100% it is. It is. I think if any of you do work in fermentation processes, it's very difficult to operate in continuous mode as one particular challenge. And if you look at any economic model for recycling or production of a product, you have to be operating in a continuous mode to really get to cost competitive prices. And so that's been something quite prohibited. And there's a lot of groups working on this that are finding ways to maybe do a design, a fermentation design that can be potentially continuous. It also requires enormous amounts of water, and it results in large amounts of biomass waste. So it is an exciting process and very useful process because we can make a lot of great bioproducts from it, but it has its limitations. There is definitely a lot of exciting work going on looking at bioproduction beyond a fermentation. What other types of bioreactors can we apply? What other types of microbial synthetic pathways can be used that don't require the same kind of fermentation process? And there's an amazing person in our team, Dr. Ali Warner, who is actively working on these types of technologies and working on how do we get bioproduction to commercially relevant and economically competitive levels. And I'll even highlight a really great company down in Houston called Solugen. They've done some creative design with combining kind of chemocatalysis with biocatalysis and biology to create bioproducts from dextrose and other sugar feedstocks. And so I think that we're innovating a lot beyond conventional fermentation to overcome some of those challenges.
I think in our last 3 minutes, I've got one probably for you, Michelle. Won't the litigation filed recently against plastic/product manufacturers impact business risk of plastics to shift focus to producers, especially given 2024 studies regarding nanoplastics human tissue burden on organs, including the human brain? But for everybody, my first thought was Michelle, but anybody is welcome to respond.
Yeah, well, there are a few different lawsuits that are pending that have been filed within the last year. A couple of them are against bottle manufacturers or, like Pepsi, and, looking at some of the public nuisance considerations or public nuisance impacts associated with those products. The other, the one that made a big splash recently was the state of California filing a lawsuit against Exxon as the biggest manufacturer of certain polymers that go into plastic production, and looking at recouping all of the different costs that California has incurred and trying to manage the pollution stemming from those products and that material design. And so if those lawsuits are successful, I mean, those are significant lawsuits that seek to recover significant levels of damages, and those liabilities are going to have to be reflected on the company's SEC filings. So that may affect, investor comfort. It may affect some shareholder considerations about, potential return on investments, things like that. And then if those lawsuits are successful, the damages, that could be recovered by those governments would be substantial. And would go a long way towards, helping ameliorate some of the conditions that we're seeing on the ground, particularly the cumulative impacts on environmental justice communities. So I do think that they have the potential to be a game changer, but those are going to be pretty long litigation battles with a lot of discovery, a lot of facts and evidence, and a lot of motions flying back and forth, to limit discovery, to try to dismiss claims and things. So I guess in short, it's kind of uncertain how those are going to turn out over time.
Thank you. I hate to cut this discussion short because there's still a lot of questions, but I wanted to thank all of our panelists for their really thoughtful perspectives. I think this has been a great discussion. We extend our gratitude to the audience and the broader community who joined us and engaged with us today. Like I said, there's still a lot of questions. We hope to continue this discussion at the next webinar. The next webinar in the series will be in December on plastic use and demand. You can register for these events, watch the historical event recordings, including this one, and stay up to date on the activities of the Roundtable on Plastics. Thank you for putting that up for us. I think that this discussion leaves us with all of us with a lot to think about. And thank you again for your time and your participation.
Thank you all.